We begin this classwork with a graph, where we're given key points and asked to find critical numbers of the function, the relative min, the relative max, the absolute min, and the absolute max. So graphically, when we want to find critical numbers, we want to look for a spot where the graph was increasing and switches to decreasing, or the graph was decreasing and switches to increasing. So as I go along, I see that here I was increasing in the graph until I got to this point, x equals -2, and past x equals -2, I'm decreasing. That makes -2 a critical number. It also makes -2 a maximum, a relative maximum. So I'm going to put relative max, -2. Again, the reason I knew that is because the curve was increasing in y value as I moved left to right, and then started decreasing in y value as I move left to right. Where that change occurs is a critical number. If it goes from increasing to decreasing, it's a relative maximum. Here, when I then change from decreasing back to increasing, that occurs at x equals 2, which is where I have a critical value that's a relative minimum. A relative minimum because it went from decreasing to increasing. Those are the only points on the graph where it turns. I do have to consider the two endpoints when I think about absolute mins and max. Absolute min and max is really where is the lowest point on the graph, where is the highest point on the graph. So the lowest point on the graph is here at -5, -42. That's the absolute min of the graph. It's the smallest value that I see. So the absolute min is x equals -5. For the absolute max, here at 314, we do have a place where it's higher and has increased at the end, but it's not the highest place on the graph. The highest place on the graph is here at the relative max, where it got to 39, which is higher than 14 in the y direction. So the absolute max is occurring at an x value of -2. When we do these without seeing the graph, we're going to need to identify critical values by taking the derivative of the function and setting it equal to 0. We can then find the critical values like this way, plug them into the original function to find the y value, but we still always have to compare it to the endpoints when we're considering absolute min and absolute max. Given an equation and asked to find the critical value, we're just going to take the derivative and set the derivative equal to 0. So for this first function, we're given 5x squared minus 10x. If I take f prime of x, 2 comes down times the 5 becomes 10x. -10x, the x drops off and it just becomes -10. If I factor this, it becomes 10 parentheses x minus 1. I'm looking for the values of x that make this 0. Nothing can make 10 0 because there's no variable involved there. But this parentheses x minus 1 would be 0 if I put in 1 for x. So the critical value that I get is x equals 1. When I try part B, I again begin by taking the derivative of the function, f prime of x. When I do that, x cubed becomes 3x squared, and -3x becomes -3. I can factor out the 3 to make it x squared minus 1, and then hopefully I recognize x squared minus 1 as a difference of squares. The difference of squares can be factored as x plus 1, x minus 1. To now find what the critical values are, nothing can make 3 0, so I ignore that factor. X plus 1 becomes 0 if I put in -1 for x. X minus 1 becomes 0 if I put in 1 for x. So the critical values of this function are x equals -1 and x equals +1. When I'm asked to find absolute extreme on the closed interval, I'm going to need to test a couple things. The first thing that I'm going to need to test is the two endpoints to see what the values are in the original function. The next thing I'm going to need to test is any critical values. So I'm going to try and find those critical values now by taking the derivative. When I take the derivative, 8 minus 2x just becomes -2. That derivative is just negative everywhere. Basically, this is a decreasing function. It's a straight line going down. So there's never going to be a point at which it was higher and now changes to low, or was increasing, changes to decreasing, or vice versa. It's just going to be negative the whole way. What that means is really the left endpoint when I put in 0 is going to be the maximum, the absolute max. When I put in 10, the right endpoint, that's going to be the absolute min. Let me show how that looks. If I try and find f of 0, that becomes 8 minus 2 times 0, which is just 8. If I try and find f of 10, that becomes 8 minus 2 times 10, which is 8 minus 20, or negative 12. So what that means is the absolute extrema, the absolute min is at x equals 0, and the value is y equals 8. I think the way that they ask you to do it in the system might be absolute max of, and then the value, oh, I'm sorry, absolute min at x equals 10. I switched these two, apologies. Absolute min at x equals 10, y equals negative 12. Absolute max of 8 at x equals 0. Sorry about that. For b, we're doing the same thing, except here there are going to be critical values. So when I take this derivative, f prime of x, it becomes 3x squared minus 6x minus 24. I can take a 3 out of each term. When I do that, it becomes x squared minus 2x minus 8. 8 is 2 times 4, so I can factor this as x minus 4x plus 2. Reason I had to do all this and take this derivative and find this factored form was to identify the critical numbers, specifically the numbers where this derivative would be 0. It would be negative 2 for this and positive 4 for this. Now I do want to check that the two critical values fall within the interval I was given. Here I was given an interval from negative 5 to 5 inclusive, meaning with brackets. So negative 2 is between negative 5 and 5. Positive 4 is between negative 5 and 5. If one of my critical values had fallen outside of the interval where I was looking for the absolute min or max, I would need to ignore that critical value. So here I have 4 values that I need to now test in the original equation. So I need to find f of negative 5, f of negative 2, f of positive 4, and f of positive 5. I definitely recommend you guys using a calculator for this. I am going to do that right now. So if I want to do f of negative 5, one of the mistakes students make is they plug it into the derivative version. Make sure you're plugging it into the original formula. So I should be doing negative 5 to the 5th, or to the 3rd, which would give me negative 125, minus 3 times 25, minus 24 times negative 5. When I do all that out, I get a value of negative 80. If I now do negative 2 cubed, that gives me negative 8, minus 3 times negative 2 squared, which is 4, minus 24 times negative 2. When I do that, I get a value of 28. When I put in 4 cubed is 64, minus 3 times 16, minus 24 times 4. When I do that out, I get negative 80. And finally, when I do 5 cubed is 125, minus 3 times 25, minus 24 times 5. I get that to be negative 70. So as you can see, I found values for each of these. When I now want to report the absolute min and max, the absolute min is negative 80, and it occurs at x equals negative 5 and x equals 4. When I look for the absolute max, It's the highest value that I returned. The highest value that I returned was a positive 28. So the absolute max of positive 28 is occurring at the x value negative 2. When we're asked to find the absolute extrema on a closed interval, we care about the endpoints and we care about the critical value that we find by taking the derivative. But one of the crucial elements to these problems is whether they use brackets or parentheses to make the interval. If they use bracket, then it includes the endpoints, and if the absolute extrema would have occurred at one of the endpoints, we can list it as the correct answer. If it's parentheses and the absolute extrema would have occurred at one of the endpoints, we don't know how close we can get without getting there. So for instance, we know that within this interval, 0.0000001 is in that interval. But we don't know that that's going to be the absolute min or max if 0 would have given us the absolute min or max, because maybe there's something just slightly smaller and slightly closer to 0 that we could say. And no matter what definitive number we put on it that's the closest number to 0, just go one more decimal place over and now we're even closer. So there will be times where we have to choose DNE or does not exist if within the interval there isn't a critical value and there's no endpoints of the interval that are included. So we're going to start by taking the derivative here. If I do f prime of x, that gets me 2x plus 2, which is really 2x plus 1, which means x equals negative 1 is my critical value. That does not occur within this first interval, 0 to 4. So I really just have to find f of 0 and f of 4. When I put in 0, 0 squared is 0, plus 2 times 0 is 0. When I put in 4, 4 squared is 16, plus 2 times 4 is 8, which gives me 24. This means with this first interval from 0 to 4, I have an absolute min of 0 at x equals 0. I have an absolute max of 24 at x equals 4. When I go to do the parentheses, again, I don't have an absolute min or an absolute max because my numbers should really be at these endpoints, and I don't ever get to those endpoints. So for this one, I would have to say absolute min does not exist. Absolute max does not exist. For negative 1 to 1, this critical value is within that interval, but really it's an endpoint which I already need to check. So maybe this problem would have been better if I said negative 2 to 1, so that way you would see that you also would have needed to check negative 1 from our critical value. But here I'm going to again find f of the two endpoints, f of negative 1 and f of 1. When I do that, f of negative 1 gives me 1 minus 2, which is negative 1. F of 1 gives me 1 plus 2, which is 3. So I found an absolute min, I found an absolute max. I'm going to list them. Absolute min of negative 1 at x equals negative 1. Absolute max of 3 at x equals 1. Again, when I get down to D and I have the two parentheses, I cannot use either of those answers because these two endpoints aren't really within the interval. So this is going to be another DNE situation. If I'd said negative 2 to 1 instead, then this negative 1 is a critical value. I could look it up and find that when x equals negative 1, in this interval it would be an absolute min. So if this had said negative 2 to 1, I could say absolute min of negative 1 at x equals negative 1 while saying the absolute max does not exist. The way it's currently phrased just gives me absolute min DNE absolute max DNE. Find the two x-intercepts of the function f and show that f prime of x equals 0 between the two intercepts. So basically what this is saying is if I cross over the x-axis, I have to go over and back at some point, which means I had to change from increasing to decreasing or decreasing to increasing. So it must be the case that if there are two distinct x-intercepts to a problem like this, then there is some point at which the derivative equals 0 between those two x-intercepts. If I factor this, I get x plus 4, x plus 2, which means x equals negative 4, x equals negative 2 are the two x-intercepts. Somewhere between negative 4 and negative 2, there must be a point at which the derivative equals 0. To find that point, I take the derivative, f prime of x. When I do that, x squared becomes 2x, plus 6x becomes plus 6, and the 8 drops off. If I set this equal to 0 after factoring, I get 2x plus 3, which means x equals negative 3. Notice that that negative 3 is between the negative 4 and the negative 2 that I identified as my x-intercepts. Little trickier when I do this one because I'm going to have some rules that I got to deal with, but where I start is by saying what makes each part of this 0 to find the x-intercepts. Well, if I just make x 0, then this x on the outside multiplies the whole root by 0, so that's going to be one of my possibilities. The other one is what makes the thing under the root 0, since we're adding 10 to it, a negative 10 would make that 0. This tells me that somewhere between 0 and negative 10, the derivative must equal 0. So let's find that point. We do it by taking the derivative of a function that is really two functions being multiplied. When we do that, we use product rule. Product rule says first times derivative of second. When I go to take the derivative of the second, it's a chain rule. Outermost function is 1/2, so the 1/2 comes down. The inner function stays the same, x plus 10. Now to the power of 1/2 minus 1, or negative 1/2, times the derivative of the inside. In this case, the derivative of the inside is just 1, so it doesn't really impact it, but I'm still going to write it here. I now need to do plus the second part of the product rule. The second part of the product rule is second times derivative of first. Second is just root of x plus 10. Derivative of first is just 1. So I'm going to write it as just the root of x plus 10. If I now go next step down, f prime of x equals this term, the root goes to the bottom, the x stays on top, the 2's on the bottom. So x is the only thing on top, 2 is on bottom, and then I have this root of x plus 10. It's being added to the root of x plus 10. If I set this equal to 0, then I can take this to the other side and make it negative root of x plus 10, and I can multiply this to that side. So what ends up happening is I have negative root of x plus 10 equals x over 2 the root of x plus 10, and I multiply both sides by 2 the root of x plus 10. When I multiply that to this side, the root of x plus 10 and the root of x plus 10 multiply together to get rid of the root. Basically, I get x plus 10 squared under a root. Squared and square root are inverse operations. So my next line really becomes negative 2 parentheses x plus 10 equals x. When I multiply out this side, negative 2 times x gives me negative 2x. Negative 2 times 10 gives me negative 20. So negative 2x minus 20 equals x. Add 3x here. Add 2x here. Add 2x here. It gets me to 3x. So I get negative 20 equals 3x, which means x equals negative 6.666, repeating, or I'm going to call it negative 6.67. Notice this negative 6.67 does fit between 0 and negative 10, which is the goal of what we were trying to show. That said, it's not directly in between them the way that this one was, where the -3 was directly in between the -4 and -2 because it was a quadratic. You can't just make that assumption. A problem like this, I need to do out all this difficult derivative to arrive at my final conclusion that x is -6.67. Rolle's theorem and mean value theorem are related. For Rolle, it says that if you have two values of x where the y value are the exact same, then at some point, at least once, between the two values, the function has to have a derivative equaling to 0. This makes sense because either it's a straight line across where the derivative always equals 0, or it goes up and comes back down to get to the other point, or goes down and comes back up to get to the other point. So here, if we want to say that it can be applied, the first thing we have to do is say that it is differentiable over the whole interval. So we'd look for things like where a root would be negative, or where the bottom of a fraction would be equal to 0, or any of these other domain restrictions or things that would make something not differentiable. Nothing like that is occurring in -2x squared plus 6x. That means I can move on to the next step. The next step is plugging in the two values and making sure that I do get the same thing for both. So if I plug in 0, f of 0 would be -2 times 0 squared plus 6 times 0, which is just 0. If I plug in f of 3, that would give me -2 times 3 squared plus 6 times 3. 3 squared is 9, -2 times 9 is -18. 6 times 3 is +18, so this also equals 0. They don't need to equal exactly 0, they just need to equal the same thing. In this case, the same thing is 0. It means that I should be able to find f prime of x. In this case, 2 comes down times that -2 and gives me -4x. X drops off to 6 plus 6, and somewhere between 0 and 3, this should equal 0. If I set it equal to 0, 0 equals -4x plus 6, add 4x, add 4x, and I get to 4x equals 6, which means x equals 1.5 or 3/2, however you want to say it. It is in the interval from 0 to 3, so I have shown that Rolle's theorem applies here with a c value of 1.5. Doing the same steps for part B here, I start by doing f of 0. When I do that, I get 0 cubed minus 4 times 0, which is 0. When I do f of 2, I get 2 cubed, which is 8, minus 4 times 2, which is 8. So again, I get 0. I can now take the derivative, f prime of x. When I do that, the 3 comes down, it becomes 3x squared. The x drops off, minus 4. So I can set it equal to 0 and find that 3x squared equals 4, which means x squared equals 4/3, which means x equals plus or minus the root of 4/3. If I'm looking for which one is between 0 and 2, it would be x equals the positive version, root of 4/3. That would be a number between 0 and 2, and this is the value of c, guaranteed by Rolle's theorem. When we talk about mean value theorem, it's the same general idea where I'm looking between 2 points and I know the derivative must do something between them. The difference is instead of just equaling 0, it equals the slope between the 2 points that we're given. What I mean by that, we're given an interval where we have x equals -1 to x equals +1. We're going to use those two values of x to solve for the associated value of y. So if I do f of -1, -1 squared is 1 times 5 is 5. If I do f of 1, 1 squared is 1 times 5 is 5. That tells me that really I have the xy points -1, 5, and 1, 5. If I want to find the slope between them, the slope would be y2 minus y1 over x2 minus x1. That would give me 0 over 2, or just 0. So really, because these were the same value, this is a case where the mean value theorem is Rolle's theorem. It's just telling me that between those two values of -1 and 1, I have a slope of 0 somewhere. If I had instead gotten the slope to be like 1/2, I would set up 1/2 equal to the derivative of f of x. In this case, since it's equal to 0, I just take f prime. So f prime of x would be 10x. And you can see at x equals 0, I would get 0. 0 fits between -1 and 1, but there's a ton of zeros in this problem. So hopefully this next one has things that aren't 0. Let's see. So if I do f of 0, that would give me 2 cosine of 0. Cosine of 0 is 1, so this would be 2 times 1, or just 2. If I do f of pi, that would be 2 cosine of pi. Cosine of pi is -1. -1 times 2 is -2. Again, I need to now find the slope between these 2 points. So the first point, when I put in an x value of 0, I got a y value of 2. The second point, when I put in an x value of pi, I got a y value of -2. To find the slope here, the slope would be y2 minus y1 over x2 minus x1. So this should give me -4 over pi as a slope. What that tells me is that at some point, the derivative has to equal this -4 over pi. So let's take a derivative. F prime of x, 2 cosine x becomes -2 sine x. If we set this up, -4 over pi equals -2 sine x. We then need to multiply both sides by pi. But you know what? Let's just divide both sides by -2. So if I divide both sides by -2, I get 2 over pi equals sine x. And this really doesn't feel right. It should be pi over 2, right? 2 over pi. I guess you would have that value for sine x. So I really just need to take sine to the -1 of 2 over pi. Make sure that my calculator is in radian mode. So let me move to radian mode. And let me do sine to the -1 of 2 divided by pi. So when I do that, I get a value of x equals 0.6901. I'm just going to call it x equals 0.69. So again, the way that I did this, I got to sine x equals 2 over pi, and I did sine to the -1, or the inverse sine of 2 over pi, equals sine to the -1 of sine x, where these are inverse operations and why I chose that. So I get x alone by putting this in my calculator, that my calculator tells me is 0.69. 0.69 is between 0 and pi, so it does fulfill what I was looking for from the mean value theorem.